Welcome to the session on application observability with Amazon Elasticsearch Service. I'm Rajiv Tauri, a principal product manager on the team. And co-presenting with me will be Thanigai Valor and Eugene Ma from Airbnb, who have built an observability solution on the service and will be sharing their case study in this session. In terms of an agenda, I'm going to give you a quick introduction, talk about the challenges that customers face with observability, how Elasticsearch Service can help. We'll then have Thaniga and Eugene come up and present their case study. And then at the tail end, we'll introduce a new feature for distributed tracing called Trace Analytics that can further extend the observability solutions that you've built today. And we'll wrap up with a summary and some next steps. So Amazon Elasticsearch Service, as a brief introduction, is built on an open source distribution of Elasticsearch called OpenDistro for Elasticsearch. And the service itself is designed to have industry-leading scalability, reliability, and security, which I'm sure Eugene and Thaniga will talk about how they've taken advantage of in building their solution. When you're looking at designing a solution for observability, the big challenge that most customers face is how to deal with the explosion of data. Telemetry data that might be coming from applications and services, data that might be coming from your infrastructure components, your IT services, etc., and then data that might be coming from your edge devices or wireless devices that are part of your broader ecosystem. This huge volume of data leads to challenges with what customers typically describe as finding the needle in the haystack. And that's the big issue in building a good observability solution. Amazon Elasticsearch Service is really well suited for solving these kinds of problems, primarily because we focus on three key characteristics. The first one being that it's designed to give you insights over analysis. So you can definitely do root cause analysis of problems that you find out. But in addition to that, you can also monitor your systems to get proactive information or alerts to issues that might be going through. So you're simply not just reacting, you're also a little bit proactive. Secondly, it's open source, not proprietary, which means that you get advantage of all of the innovation that's happening in open source. We innovate in open source as Amazon. The community innovates in open source, and our customers who have adopted open source may also innovate on it, and all of this innovation is now available to you. And thirdly, we built in machine learning capabilities, and it's not just simply rules-based, which allows the system to be really adaptive to the changing environments. Moreover, machine learning capabilities can help you predict outcomes that oftentimes might take multiple lifetimes for a human being to uncover, and dealing with these large volumes of data makes it particularly suited for those applications. So with this, I want to now introduce Thanigai to talk about Airbnb and how they've taken advantages, how they've built on these three strengths of Elasticsearch Service as part of their observability solution. Thanigai, welcome.
Hi. Today, my colleague Eugene and I are going to provide an overview of the application logging infrastructure used at Airbnb. We will share our experience and walk through the challenges inherent to the logging infrastructure and highlight a set of principles that helped us build a scalable and efficient infrastructure. We will then provide an overview of the architecture and go over the individual components of this infrastructure. Logs provide critical insights to better understand application behavior, performance, and user experience. Logs are key in reducing the mean time to resolution for incidents. The application logging infrastructure at Airbnb processes and stores logs emitted from several hundreds of services. We store more than 300 terabytes of log data per day, and the infrastructure is used by thousands of engineers for debugging purposes. Now let's review some of the challenges we faced when building such a large-scale infrastructure. The challenges can be broadly grouped into three categories: integration, operational, and organizational. When it comes to integration challenges, the infrastructure needs to support different types of integrations, both on the write path and the read path. On the write path, the infrastructure needs to support a wide variety of compute environments such as EC2, Kubernetes, serverless, and so on. In addition, we have to support multiple log formats that are emitted from different types of services. On the read side, the infrastructure needs to support different consumption models for log search, analytics, and visualization. The second category of challenge is operational. We have a very dynamic environment where the traffic pattern and log volume can be spiky. Also, the operational overhead required to manage this infrastructure can become a challenge if proper automation controls are not in place. On the organizational side, it is very critical to have visibility into the total cost of ownership and provide a showback model for the cost to the teams that use this infrastructure. In addition, there are varying log processing and retention policies for different tenants that needs to be managed. In order to address these challenges, we adopted some architecture principles while building this infrastructure. And today, we would like to highlight three principles. The first architecture principle is modularity, which refers to the degree to which the components of the infrastructure can be separated and composed together. The infrastructure is composed of different subsystems where each subsystem is responsible for a specific concern. By having clear separation of concerns, each component has a specific responsibility, which makes it easy to compose them together for different use cases. The second principle is efficiency. An efficient logging infrastructure means less waste. And this efficiency needs to be applied across different dimensions such as cost, performance, and productivity. We rely heavily on automation and building self-healing closed-loop components that can adapt to changes in traffic or usage. Now moving on to the third principle, we have multi-tenancy. The infrastructure is a centralized platform that is used by many teams. The teams have different logging volumes and different processing requirements. Thus, it is very important that we build the right controls that can provide the necessary isolation and governance for each tenant using this infrastructure. Now let's review the architecture of the logging infrastructure. At a high level, the infrastructure is composed of 4 tiers, organized based on the different stages of log processing. The 4 tiers are collection, ingestion, storage, and user interface. These tiers are composed together to create the logging infrastructure cell. We enable a cell-based architecture to stamp out multiple instantiations of the stack where each cell is independent of other cells. This allows us to easily scale this infrastructure to onboard new use cases. Now let's review the individual tiers at a high level and see how they interact with each other. The collection tier is responsible for collecting logs from different data sources and forwarding them to the ingestion layer. We use FileBeat as the default log shipper for most use cases. FileBeat provides a lightweight mechanism to monitor the log files and collect and forward them to the ingestion tier. The ingestion tier has two components. We use Amazon Kinesis as a durable buffer to store the incoming logs. The logs stored in Kinesis are then ingested by Logstash service. In Logstash, we apply a set of plugins to enrich and normalize the logs into a standard format. Logstash forwards the transformed logs into the storage tier, which is responsible for indexing the logs and making it available for search. We use Amazon Elasticsearch for the storage tier. Amazon Elasticsearch is a fully managed service that makes it easy to deploy and run Elasticsearch efficiently at scale. Moving on to the user interface tier, each Elasticsearch cluster is configured with Kibana, which allows engineers to explore, search, and visualize the logs stored in Elasticsearch. In addition to Kibana, the logs are made accessible for search in an internal tool called Watchpoint. Watchpoint is an all-in-one observability tool that brings in metrics, logs, and traces from different sources into one tool. We will now review these tiers in more detail. Now let's review the collection tier. The main purpose of the collection tier is to provide a standard interface to collect all types of logs from different sources. We use FileBeat as a standardized log shipper. FileBeat is deployed in a distributed agent model, either as a sidecar or as an on-host agent. Application logs are typically written to standard out from the producers, which gets forwarded to local files on each node. FileBeat monitors these log file locations, collects the logs, and forwards them to different destinations. We have developed a custom output plugin that forwards those collected logs to the respective Kinesis streams. Now let's see how we adopted the 3 architecture principles that we reviewed earlier. When it comes to modularity, the collection tier is solely responsible for log collection from different sources. The collection tier supports structured JSON-based logging, which allows teams to publish logs in a standard manner. In addition, the logs are formatted and enriched with metadata useful for log filtering. The logs are also injected with fingerprints that makes it useful to understand the source of log volume spikes. By building these capabilities into this modular component, we get consistency across all logs ingested into this infrastructure. We built several optimizations on the collection tier that makes log collection efficient. As I mentioned earlier, we developed a custom output plugin in FileBeat that sends log records to Kinesis. We enabled batching of the records that are published to Kinesis. By batching log records, we are able to significantly reduce Kinesis costs. We have also developed custom probes that are enabled for all services. This measures ingestion latency across different stages of the log pipeline and provides closed-loop monitoring, which is useful for auto-scaling the infrastructure. As a multi-tenant infrastructure, the collection tier provides standardized interface for all tenants to configure the log pipeline for their services. It provides the ability to specify the fields in the log that needs to be parsed and indexed. In addition, tenants can configure quotas, which is used to provision the ingestion capacity for their services. This feature, combined with closed-loop monitoring, provides the necessary control loops required for tenants to be autonomous. Now I will hand it over to my colleague Eugene, who will walk through the rest of the tiers.
Thanks, Thanagai. Incoming logs are buffered in the ingestion tier. The buffer protects us against data loss when the storage layer can't keep up with the ingestion rate. We chose to use Amazon Kinesis for the buffer because it's fully managed, so we don't have to maintain any services ourselves. On the other side of the Kinesis stream, a stateless, horizontally scalable pool of Logstash instances will process the logs in the stream. Processing includes geolocation by IP, parsing third-party log lines, and scrubbing sensitive information. Following the normalization step, Logstash writes events in batches to Elasticsearch through the bulk API. In our experience, logging volume can be very unpredictable. Excessive logging volume is often introduced without anyone noticing until ingestion falls behind. At this point, our users can't see logs in real time, so the on-call for our team gets paged. The on-call engineer then has to manually investigate and identify the service generating the unexpected log volume. These incidents can happen quite often in a service-oriented architecture due to autonomous and frequent releases. In a multi-tenant environment, this problem is known as the noisy neighbors effect. To solve this problem, we need a way to control ingestion volume for each tenant and isolate the blast radius of noisy neighbors. In other words, we need some way to enforce fairness among tenants. To enforce fairness, we introduced logging quotas. We implemented this by partitioning our Kinesis streams and giving a dedicated stream to each tenant. Each of these dedicated streams has a fixed number of shards, which defines the tenant's logging quota. These logging quotas are enforced through the automatic throttling mechanism built into Kinesis shards. Alerts are automatically routed to tenants when their streams are throttling excessively. Tenants can then use tools to increase their quota, which resizes the underlying Kinesis stream, or find ways to suppress the noisy logs. All of this can happen without involving the observability team. This significantly reduces operational burden for our team and achieves a form of self-governance among tenants. At our storage tier, we persist our logs and make them available for searching and analytics. We chose to use Amazon Elasticsearch for its simplicity in terms of management, scalability, and security. As Airbnb's logging footprint grew, there were two approaches to scaling the storage tier. The first is the monolithic approach, where you continue to scale a cluster by adding more nodes or larger instance types. However, in our experience, running massive Elasticsearch clusters was operationally challenging. We then shifted to a different approach, which involves physically sharding the data across multiple clusters. In Airbnb's service-oriented architecture, queries are usually segmented by service, so we decided to shard the logs by service. Sharding our architecture this way meant we were no longer bound by the limits of a single Elasticsearch cluster. Instead, we have many smaller clusters which are individually easier to manage. Furthermore, a lot of the heavy lifting for each cluster is already handled by Amazon Elasticsearch, such as software updates and self-healing. However, there are still higher level decisions to make for each cluster. For example, how many nodes to use? What instance types? How do we partition our indices and load balance shards? How can we optimize cost? Our main rule is to treat our clusters more as cattle rather than pets. Pets are systems that require special handling for each instance. This doesn't scale well when you have so many clusters. Cattle are systems whose instances look the same and can share the same processes and tooling. Consistency enables a greater degree of automation, which in turn enables you to scale cluster management. By adopting the mindset of cattle over pets, we went from managing a few huge monolithic clusters to managing about 45 small to medium-sized clusters. Next, I'll discuss specific strategies we implemented to achieve cost efficiency. The lowest hanging fruit was switching to the most aggressive compression algorithm. This decreased disk usage by 20%, which translates directly to cost savings if your clusters are storage bound. Next, we enabled AWS UltraWarm, which adds a warm storage tier for logs. Logs in UltraWarm are cheaper to store but slower to access. This is perfect for historical logs since they're rarely accessed compared to recent logs. To keep utilization within the desired range, we have a tool that computes the optimal sizing of each cluster based on its current CPU and disk utilization. With the managed nature of Elasticsearch, resizing is a lightweight process on our end, and we usually run it about once a week. Lastly, we've observed that our users have diverse retention needs. Rather than enforce a blanket retention policy, we let users choose their desired retention. This can be done within a cluster by writing to different indices. This strategy allowed us to adopt a very conservative default retention while still providing a longer retention option for users that actually need it. Logs are primarily accessed through Watchpoint, an internal monitoring tool created by our team. Because the storage layer is sharded across multiple clusters, one purpose of Watchpoint is to federate these clusters. Users can search for logs from a specific service or search for logs correlated by a common trace ID. The underlying cluster sharding topology is hidden. The second purpose is to provide a Kibana alternative that streamlines the log searching experience and integrates logs with other observability data, like errors and traces. However, there are certainly cases where a user may need the full power of Kibana and Elasticsearch. A Kibana instance is bundled with each Amazon Elasticsearch domain. Users may go to Kibana directly or access it through links embedded in Watchpoint. These links include pre-populated filters, which reduce query load on Elasticsearch. We started this presentation by discussing some of the challenges in maintaining a scalable logging infrastructure within a large organization. To close the loop, let's revisit these challenges and discuss the impact of our efforts. Our logging infrastructure can ingest logs from a variety of runtime ecosystems, such as Kubernetes, EMR, and even CDN providers and other cloud services, while reusing most of the stack. In addition, we have built custom UIs which integrate logs with traces and metrics. On the operational side, we reduced our Amazon Elasticsearch costs by about 60% through the cost reduction tips mentioned, and by provisioning resources elastically. In addition, the support burden is very light. It requires only half an engineer to keep the lights on and maintain cost efficiency. And we can deliver this service with 3 nines of reliability and sub-second ingest latency. Finally, through self-governed logging quotas and retention policy, we prevented log volume from growing faster than the business. Lastly, I'd like to appreciate some people who helped make logging successful. Rong Hu led many foundational efforts, such as building the log shipping layer and migrating to Amazon Elasticsearch. Xuan Liu designed and implemented the logging UI built into Watchpoint. Amulya Sharma is a solutions architect who worked with us to reduce Elasticsearch cost and continues to be a valuable partner. That concludes our part of the presentation. Thanks for watching.
Thank you, Eugene. Thank you, Thanigai, for a terrific presentation on what you've done with Airbnb. I'd like to now build on what Eugene just shared with their Watchpoint tool on how they've integrated traces, logs, and metrics into a single solution. We've learned from that, and we've extended Amazon Elasticsearch Service and Open Distro for Elasticsearch with a capability for distributed tracing called Trace Analytics. What this really allows you to do is to have one single place where you can visualize both your trace and log data and flip and switch back and forth between them, where if you found out some issues with tracing, you can use your trace identifiers to navigate to specific log events that might correspond to it. The views that we have in Kibana that we built out of the box for it include the traditional views of helping you navigate to a particular trace and span details for each individual trace. So you can look at the performance end to end, and you can very quickly identify the root cause down to a particular service node or an execution path which might be problematic. But in addition to that, we have aggregated information from all of the traces that we collect to give you end-to-end visibility into your applications. This is done in 2 ways. One of them is to give you a service map, which in a graphical format represents each of the service nodes that make up your end-to-end environment. And we automatically assemble performance data for those service nodes from the raw trace data that we collect. And then secondly, we also assemble trace groups. Now, a group is a collection of similar traces. We use service and operations name as the identifier to name a particular group, and then we monitor performance for it. So you can be quickly alerted. For example, if you're looking at all your login traces, you can quickly find out if the error rate for your login traces has gone up, or if they're taking particularly long to execute, and then dive into specific instances of logins that took long to execute or had errors to find out what might be going on. With that, let me give you a quick demo of what this visualization looks like in real life, and give you better insights into it. So we built a sample app here for purposes of this demo. Clicking on any of these buttons will execute a transaction. That transaction is captured as a trace in the trace analytics solution. For purposes of the demo, I've gone ahead and already executed a whole bunch of transactions and pre-recorded them. And now I'm going to show you how to visualize all of that individual trace data in Elasticsearch. So the first thing that you're going to see is a view of all of the traces, the collection of the service maps, as well as the trace groups out there. So what you see here is a list of all of the traces that have been captured in the system. Each of the traces has been identified by a unique trace ID, and we capture the relevant performance information for all of those traces. In addition to that, you can see we've assembled information about each of the individual traces on our main dashboard and services tab, which we'll navigate to and show you what that looks like. So in the main dashboard tab, you can see that we have a collection of traces by trace group. As I mentioned earlier, each trace group is identified by a service and operation name. So all traces that share that characteristic are part of that group. We capture the key performance information for each trace group. And most interestingly, in this scenario, we've also configured it to identify the P95 performance. So the 95 percentile, so you're not only just looking at averages, but you can look at your P90 or P95 performance for each trace group, and the individual traces that correspond to it. By clicking on the P95 performance, I can automatically filter all of my views for that particular subset of traces. So I can see, for example, at this point, I've selected the 95th percentile trace group and my client checkout trace group name as the filters. And I can see here that one trace corresponded to that particular group. I can click in and drill into it and see that what that looks like. The filters that I had set on the previous page are carried forward here. You can see the latency performance of that particular trace. I can click into the trace to look at the trace and span details for that. We've done two interesting things here. We've characterized the performance of that individual trace by the time spent across all services, as well as capturing all of the trace and span details for that particular trace. It's interesting to capture the time spent by service, because you might have multiple spans executing for a service. You might be making multiple calls to a particular service node, or you might have spans that are both inter-service as well as intra-service spans. So it's oftentimes useful to just view a pie chart of what the service breakdown looks like. And then finally, we also have the full payload information for that particular trace with all of the attributes for it. You can grab anything, any of the attributes, and search for it further from there as well. And the last thing worth seeing is obviously the service tab that we talked about. So on this view, you have both a list view of all of the services that make up your end-to-end application, as well as a service map with an end-to-end view for it. The list view shows you allows you to select the service by name and to sort it by performance or throughput, for example. The end-to-end view helps you visualize the upstream and downstream components of all the services that you might be interested in inspecting further. So this is a great way to identify what was going on. With this, we hope for each of the service nodes, obviously, we also capture key metrics like latency, error, and throughput, which gives you a quick insight into what the problematic service nodes might be in your end-to-end environment. With this, we hope you got a good overview and demo of what this feature looks like. We hope you'd give it a try. Download it, try it, use it, give us feedback, and even contribute to it on open source to make it work. Now that we've seen the demo, I'd like to show you what the data pipeline for trace data might look like in your open distro for Elasticsearch environment or your Amazon Elasticsearch environment. Obviously, for a generic data flow pipeline, you might have a number of producers. Today we support a range of collectors, such as FluentBit, FluentD, Beats, Amazon CloudWatch, and Kinesis agents, for example, as well as a whole slew of aggregators, Logstash, Amazon Kinesis Firewalls, managed services for Kafka, and some customers even end up using S3. Tanika and Eugene obviously talked about how they're using some of these components as part of their data pipeline. So I'm going to show you how do you extend this for trace analytics. For trace analytics, we actually added support for 3 specific types of instrumentation libraries: Jaeger, Zipkin, and OpenTelemetry SDKs. For collectors, we added support for an OpenTelemetry collector. All of these libraries work with the OpenTelemetry collector. And the OpenTelemetry collector is directly able to communicate with Elasticsearch. So we don't need a separate aggregation layer here between OpenTelemetry collector and the Elasticsearch service to make it work. For those of you that are not familiar with OpenTelemetry, OpenTelemetry is a CNCF project. It was formed with the merger of OpenTracing and OpenSenses. Jaeger, for example, Jaeger and Zipkin were part of the OpenTracing and the OpenSenses projects, and both of them are moving forward with merging themselves into OpenTelemetry and supporting the OpenTelemetry standard. In addition to supporting the Jaeger and Zipkin libraries and SDKs, OpenTelemetry itself is also developing its own SDKs and libraries. Today they support 11 different languages and probably more every week. We support all of these SDKs and any instrumentation library, in fact, that's compatible with OpenTelemetry. The trace data that's captured by these libraries flows through the OpenTelemetry collector via an exporter to Elasticsearch, OpenDistro for Elasticsearch, or Amazon Elasticsearch service to be monitored. Now, in addition to using any of these open source components, Amazon itself is also making available a distribution which is called as the AWS distro for OpenTelemetry. It's essentially the open source distribution. All of our contributions are in fact first made into the open source project. So we have an open source first and an upstream first contribution policy with regards to this. The main advantages with AWS distro for OpenTelemetry is really the fact that it is supported by AWS. It has been certified by AWS for security, and we have worked with it to enable one-click deployment into AWS containers and Lambda consoles. So if you've got services running in any of AWS, these infrastructure components, you can very easily deploy these OpenTelemetry collectors and SDKs into your application and configure it for monitoring. Now, in addition to supporting Elasticsearch service, we also support CloudWatch for metrics and X-Ray for trace data. So with OpenTelemetry, you have a choice of monitoring services available for you. With that, I hope you've gotten a good sense for what trace analytics looks like and how to build an observability solution using traces and log data. To learn more about it, please do go to the homepage links for OpenDistro for Elasticsearch. On that, there's also a developer portal if you'd like to contribute. The roadmap that we use for trace analytics and other enhancements on OpenDistro is fully public, so you can access the roadmap there as well. And if you do try it out and have feature requests or issues that you'd like to discuss with us, we have a forum that we're pretty actively engaged on. You can go to the forum as well and take care of that. So hopefully, as part of this presentation, you got a good overview of how to build an application observability solution with Elasticsearch and how the principles of working from insights, being open, and using machine learning capabilities is going to help power you to build out-of-the-world solutions for application observability. I'd like to thank Taniga and Eugene once again for agreeing to co-present with me, and look forward to speaking some more with you folks. Thank you.